Hello, Thomas.
Hello, good afternoon.
Good afternoon. You can hear me, yes?
Yes, I can.
Okay, perfect. Yeah, that's good. Just to get your consent, we are going to record the lecture if it's okay with you.
Yes, that's fine for me.
Perfect. Okay. Good. Okay, we wait until 3 to get all our participants, then we start. Hello. Is Gregor coming here?
I don't know if we come here. Yeah, he was there this morning. It's 38.
38.
I was looking at it.
I was not same thing happened to me. I wrote marking, but it was a typo.
Two people online already, right?
Yes, we can. So it's 3 now. We can already start. 3 people are joining. can we leave this open so, or maybe if someone wants to come. Okay. Okay. Hello, everyone. Welcome to the inaugural lecture of the Energy, Sustainability and Circularity Seminar Series organized by the Department of Chemical Engineering, University of Liège. My name is Motia Rahman. I'm an assistant professor at the Department of Chemical Engineering and the coordinator of this lecture series. The main idea behind organizing this seminar series is to listen to the world leaders on a range of topics related to energy and sustainability. Before I introduce today's speaker, I would like to kindly invite the Dean of our Faculty of Applied Sciences, Professor Eric Delège, to say a few words about the seminar series.
Thank you, Motia, for this introduction. Well, good afternoon, everybody. I'm delighted to open this seminar series because I'm sure I love the format first. I think it's very interesting to be able to connect through with a large audience going far away, and to be able to exchange ideas with as you said, top speakers. Nobody would like to have meetings that are fully online, but for short discussion, for a short presentation, that's very, very convenient. So I like this. I think also the topic is very, very interesting, very important. And it's getting more and more timely as time goes by. I mean, for a while, sustainable development has been something like, well, a kind of dogma. Of course, it's important to support the development of technology that preserve our environment, but things go far beyond this today. I mean, we are the witness of the importance of raw materials and energy in a geopolitical view of those topics. And that's why things become major now. We have to be able to, use our resources as smartly as possible, I would say. We are the witness of a big try by, let us say, the US, for instance, to put the hands of the resources in other countries. We in Europe have not that many raw materials and raw resources, and we are forced to be one step beyond, I say, to be in advance with respect to these problematics, and to prepare the future in a way that's both sustainable for our environment, but also for our society and of our well-being. So this makes it very appropriate. So I think this topic is very interesting. It's also very interesting for me as the Dean of the Faculty of Engineering at our University of Liège, because those topics also are at the center of many different initiatives in our university. And bringing together people that come from different horizons with different expertise to tackle those important issues is also something very important. So I'm very happy to see this wide audience today. I hope we can meet on site, say at some point you never know. But most importantly, I want to thank and congratulate Motia for bringing you together and setting this on track. So I wish you all the best and enjoy the presentation that will be given today and the next presentation that will be given during the coming month. Thanks again. Enjoy your presentation.
Thank you very much for your kind and encouraging words, Eric. Now, I would like to request the president of our department, Professor Gregoire Leonard, to say a few words.
Okay. Thank you very much, Montier. We are in the same room. I arrived just a little bit late, but we are in the same room, and I'm very happy that you invited me to this honor of introducing you to the seminar series, and I'm very happy to be supportive also of what you've been launching here. I think this is really part of our job as well, and often we overlook that too much. To be able to communicate, to be able to discuss with our peers, and to be able to present our results. We've had at the beginning of the week a very nice visit here at the University of Liège. You met with Professor Burdyny of TU Delft from Johns Hopkins, and he was telling me, you guys are doing amazing things, but nobody knows about that.
Exactly.
And this is the point of this kind of event here, to say, okay, we are here to share a little bit about our results, and we are here to invite people to share about their results, because this is the way that you can create really innovative ideas and impact on the society, which should be our goal also as engineers and as researchers. So thank you again for implementing this. I'm wishing you and all the people who are attending a very pleasant session. I also would like to thank very much Professor Burdyny, who has agreed to be the first speaker for this webinar series, and I wish us a lot of success with those series, and I'm pretty sure that it will be. Thank you very much.
Thank you, Gregoire, for these exciting words. Well, now let me take the opportunity to introduce our speaker. Professor Thomas Burdyny. He's an associate professor of chemical engineering at the Delft University of Technology, the Netherlands. He obtained his B Engineering, Bachelor's of Engineering, and Master's in Mechanical Engineering from the University of Victoria in Canada in 2010 and 2012, respectively. He then received his PhD in Mechanical Engineering from the University of Toronto in Canada in 2017. He then started his independent career as an assistant professor at the Delft University of Technology in 2019, and then promoted to associate professor in 2023. His group's research takes a problem-centered approach using a mixture of measurement techniques, catalytic design, interface engineering, and transport optimization to advance electrochemical technologies. Thomas has received a number of awards and individual grants, including the Dutch VENI and VD grants, as well as the prestigious ERC starting grants. Without further delay, I would like now to invite Thomas to take the stage. Thomas, please.
Yes, thank you very much, Montier, for the introduction. Can you see my screen in presentation mode?
Yes.
Perfect. Thank you very much. Today, I'm very happy to be here for this inaugural lecture of the series, and I decided to choose a topic that's very close to my heart, not only electrochemical research, but specifically how we can design and choose research challenges. I am a believer that not all research nowadays, unfortunately, follows more of a scientific method approach. And I want to kind of introduce how we tackle research and really try to motivate research to take the path that is the most impactful, but also the smoothest for our researchers. To give you a kind of a larger perspective, so my group at TU Delft, we take, let's say, one of our larger questions is how do we advance the technology of CO2 electrolyzers, so devices that convert CO2 into value-added products? How do we actually scale up this technology? And what are the barriers impeding that? So you can imagine that we perform research on the watt scale, but if a technology is going to help in our society, we really need it to be working at the megawatt scale. So what we can do is we can design and think of problems. Well, how can our small cells actually do research that is relevant for larger scale systems? You can also look at it from the other way, where say if we have the watt scale and we have the megawatt scale, what is acting in between these two that prevents commercialization or prevents scale up? And then you can also do thought experiments where you say, okay, I'm going to imagine what a megawatt scale electrolyzer looks like. How will this size and this physical object, how will this scale change how we should operate our devices at the small cell? So how can we translate that thinking back and forth? And you can imagine these individual questions can be broken into individual projects or individual papers. And this is more of, let's say, at a lab scale. So if whether or not you're an individual researcher, so a master's student or a PhD student or a postdoc, or if you have an entire research group and research line, you can ask yourself, how should I come to questions that can be used as a framework for my own electrochemical research? And let's say the approach that we take, we try and think, how can we choose a project or a research line that is not only novel, it's impactful, so it's impactful for research or society or industry, while also being low risk. And these three things might seem like they don't go together, but my job for the talk today is to convince you that you can have novel, impactful, and low risk research projects in your group or for yourself. So how do you do that? So let's say the first post here, your starting point. So let's say even before you perform any research or even start a PhD or even join a research group as a master's student, where do you start? For me, I think that actually the most important thing is to first determine for yourself what you care about. So what motivates you internally, and really, research is bumpy, research is rocky. When you have those periods of time, what internally will keep you going and drive you? For me, for example, it is to be a good and reliable supervisor. So I never want my PhD or master's students to feel that I'm not there for them. I want to work on research that contributes to the energy transition. I want my group to be known for having excellent researchers coming out of it and being able to trust the research that we do. And ideally, I also want to inspire others to pursue similar research. So we are one research group. We publish maybe 5 to 10 papers per year. Ideally, we inspire people to do other similar research such that our reach is far beyond our own active work. So I encourage everyone to identify your own internal drivers. And this is, let's say, the first point to have an impactful research project. Next, you will then want to identify a technology or research area that aligns with these drivers. So for me, this right now has been quite a large foray into CO2 electrolysis and adjacent electrochemical technologies. And the really idea is to push this technology towards implementation or to keep pushing it towards the next scale, or for that matter, to extinction. So if we find a part of a key energy technology that we think will forbid it from being scaled up, then we would also want to communicate these views as well. So once you have a larger research field, fields are very large. If someone says I'm working in water electrolysis, someone else in water electrolysis won't say, okay, they'll say, oh, what field of water electrolysis? Are you working in PEM electrolyzers, membrane manufacturing or stability? You're working on catalysts. So every larger field has a subtopic of field. And in those individual subtopics of field, you typically have, let's say, clear technological barriers in that field. So it's important to really understand this and, let's say, understand the heartbeat of the research you're working in. Research is fundamentally performed by humans, and understanding what is barriers or what people are interested in is quite important to do. So as an example, in CO2 electrolysis, you can be working on catalysts or membranes, you can work on stability, you can be doing new kind of fancy chemistries, or you can be doing, for example, scale-up activities. Now, once you've identified a barrier, then you want to essentially say, well, this barrier exists. It exists for a reason, and you can hypothesize, well, how can we overcome this barrier? Is it a technological problem? Is it a fundamental problem? Is it we don't understand something? Is it a material problem? And once you really, really dig deep, then you can really come up with new hypotheses for how to overcome that. Then what you should, of course, do is then test your hypothesis versus literature. So there's thousands of papers in most research fields in CO2 electrolysis. I think 3,000 papers are published a year in the domain. So there's a good chance that someone has performed an experiment that you have already hypothesized, and maybe they've generated data that they haven't looked at a certain way. And once you really have a hypothesis, you can usually test it versus literature. So for me, this is great because you're collecting data without actually having to do it yourself. Lab work is very time consuming, and ideally, if someone's done it for you, that's the best place to be. Then, kind of sticking to core philosophy, you should, if you truly understand something, you should be able to do a simple experiment, simple in quotations, to test that hypothesis as sharply as possible. And that really is where you have the start of an impactful research project. Now I'm going to pose an open question, so feel free to type in the chat or say aloud. These last 4 steps that I put here, is this groundbreaking? Did I invent this, let's say, line of thinking? What does this remind you of?
Should be the case of new researchers. When you want to address the field, it makes sense to look a little bit about what exists already, what you want to do. So I think it's very good practice to do that.
Yeah, and what I'm describing here is really just kind of the classical scientific method where you have some kind of observation. So your observation could be, well, there's a barrier that exists, and then you could ask a question, well, why does this barrier exist? And I really think continuously going back to a scientific method approach helps to make things as smooth as possible. And what's really important for me is I really think that this part of what barrier you choose or what hypothesis you come from, this is really the upper bound of a typical research project's novelty or impact. And this is where you really define how impactful your project will be once you complete it. Now, that doesn't mean that you can't do things like stumble across graphene or let's say, stumble into a new discovery. But that is not how most research works. Most research, let's say, novelty decreases over time. So where you frame up your project really determines where you'll go from there most of the time. And what's really important from my research approach is that you ideally, let's say, follow a deductive reasoning approach. So you've already come up with a hypothesis, and you have an idea of what your conclusion should be, and then you can design an experiment to test that hypothesis. And when you're doing this, I really think then you can do research that can be completed in, let's say, 50 experiments instead of 1,000 experiments. What I see a lot in papers is more of an inductive reasoning approach where people generate a whole lot of data and then look for a pattern and then write a paper or make a conclusion based upon that data. I prefer an inductive reasoning approach once you've already narrowed your initial hypothesis, and it's good for, let's say, refining things further. So I'll talk a little bit more about this later in some examples that we had in the past. But yeah, I'd really say that going to the lab and collecting data is a surefire way to have a potentially stressful research project. So I really encourage going to the lab with a very specific hypothesis in mind and doing a short experiment to try to test that as sharply as you can. Now, I mentioned novelty and impact. I think it's worthwhile dwelling on this because when we talk about academic publishing or applying for grants or having people, let's say, being interested in your work, it comes down to generally novelty and impact. And I'll explain what these are and why I care, for example. So let's first go to the textbook definition. So what is novelty? So novelty in research is simply something that is new. But then the question is, what is new? And has anyone seen this image before or come across this in the past? So I came across this when I was doing my master's. So when I was kind of interested in research, and it's kind of a pictorial representation of what is research or what is novelty. You can kind of think of all of human knowledge within this kind of circle, and then as you get more and more specialized and you do more and more research, you kind of go into a small branch of all of human knowledge. And really, if you zoom in on, let's say, what is electrochemical knowledge, this little bump here is really what a PhD is, and it's the novel creation of things for humanity. So this is in a way what you can define as novelty. And a paper or a PhD should meet this threshold. Now, novelty is in reality not a binary yes or no. You could really say that there's a scale of novelty to some degree. For example, someone might say, well, Something that's novel is a new technique that is very specific to a singular specialized field. So say I invent a new characterization technique, but it only works in situ electrolysis, you might say that's a relatively small novelty. However, if it's applicable to all electrochemical technologies, then you'd say, oh, it's a little more broad. It's more novel, people would say. And let's say it applies to all analytical chemistry, then you'd say the technique has broad novelty. So that's kind of a scoping of that. Next, we have impact. So what is impact? Scientific impact is some kind of short or long-term influence that a finding has on science or society. There's lots of different types of impact. Most of the time, most of what we do in a university setting directly corresponds to academic impact that then over time snowballs into societal or industrial impact or economic impact. And this is where we come kind of to our focus on sustainable development goals. So when we write grants or when we talk to people, we say, well, what sustainable development goals are we contributing to? And so every kind of little piece of work is moving towards that. The type of impact that I really like to have is when you can change people's thinking or perspectives. A lot of the times, if you want to change people's behavior or let's say motivate things on a political spectrum, the best way to do it is you change someone's kind of worldview or how they think about something. So in our research, I really like when our research can say, direct the research that other people do, even if they don't directly use our scientific findings. That's usually by changing people's perspective on a topic. So now you can take these novelty and impact, and let's say you can put it on a spectrum. Here I've talked about it from electrochemical fields, but really it works for any scientific domain. You have impact and you have novelty. And you can kind of say if you have little impact or little novelty, then generally your work will struggle to be published. If you have, let's say, some spectrum of novelty and impact in this purple region, then you can say, well, your work will be published in a reputable or visible journal. And then you can even go, let's say, in this higher impact and higher novelty where your work is not only easy to be published, but is likely a well-recognized paper in a field. So who here has gone to academic conferences? So feel free to thumbs up in the chat. Most people conferences, yes. So you finish a long day of conference talks. Let's say you've had maybe 20 talks during the day, and then you kind of stumble into the cocktail area, maybe grab a drink. You go one of those round standing tables. A couple of your colleagues or colleagues in the field or from your lab stumble up, and you just start talking about research. And then you say, oh yes, oh yeah, you saw that paper by Lee. They did this capillary effect work. And then the other person says, oh, yeah, I recognize that work. So with very few word descriptors, for example, someone might recognize a paper. That's what I mean by, let's say, a well-recognized paper in the field. It's a work that almost everyone in your domain has read and understands. What's important to know is when you talk about reviewers or editors, let's say your novelty is typically your novelty versus your short-term impact. Typically, long-term impact is harder to reward in science. So in electrochemical fields, we see a lot of emphasis on performance metrics, so really numerical metrics. Why is that? Why do we care about Faraday efficiency or voltage or stability so much? Feel free to unmute or type in the chat. Why is so much of a lot of STEM fields based on numbers and numerics? The solar cell efficiency chart by NREL that tracks solar cell efficiency for different technologies. Why is this so common in the field?
Because it's easy. It's easy to compare, right?
Yeah, so I think in practice that's certainly the case. That's certainly why most people do it. In principle, and this is not done often enough, but in principle, the reason why we care about performance metrics for energy-related technologies is, in theory, they link directly to the capital and operating costs that would be required for that technology to take place. So if we look at electrolyzers, the efficiency or the current density can link directly to how large a system will have to be and how much you have to pay to keep it running. So that's why if you look at batteries or solar cells or electrolyzers, you always have, let's say, a set of performance metrics that people like to talk about. And this is in theory linking to the capital and operating expenditures of a technology. So for example, selectivity or production rate. And even for different energy generation technologies. So for example, the levelized cost of electricity is common when you compare different technologies, and you see a lot of news articles. Solar and wind are cheaper than fossil-based things, for example. And in general, the more cost competitive a technology is, the closer it goes to the business as usual case, and the closer it can take over an existing market. So when we look at a lot of literature, there's a lot of focus on let's say, these performance metrics. Now let's zoom in on this triangular region here and say, what are different types of categories of novel and impactful? And I think this is useful to talk about, to consider, let's say, categorize the types of papers you might read about. So one classic example is the case, say, there's this orange circle where you have a very, very big performance advancement. So numerical advancements is achieved, but frankly, without little clear insight. So yeah, this really falls into the fancy catalyst category, where catalysts appear to have very, very great performance, but there's not really a clear control or proof as to why they're doing so. This makes them not only hard to reproduce, but then this makes it less impactful. You can then have, let's say, this green region where you have some kind of big performance advance. Maybe it's system-wide or catalyst-wide, but this is enabled by fundamental insights. So there's a new fundamental understanding that then allows someone to make a big performance advance. Now everyone can take advantage of that and then accelerate the overall field forward. So that's where something has high novelty and high impact because it can be used. You then have, let's say, the other spectrum down here. So I kind of like to think of this as like the classical papers in Joule. So the journal Joule does a lot of, let's say, larger scale demonstration work. And there's something where you can have a large physical scale. It shows that a technology is advancing industrially, but maybe it's not based on any novel work, but it was, let's say, more of a demonstration work. So let's say these are some extremes you might see in the electrochemical field. Then you might have something more, you have a clear fundamental insights for a specific electrochemical technology. So maybe CO2 electrolysis, you make a new insight. And you can imagine that if that insight is actually applicable to multiple electrochemical fields, then you can imagine that the impact goes up. So my research field is mostly in CO2 electrolysis, but what we do for a lot of our work is say, is this actually applicable to many different small molecule conversion technologies, such as water electrolysis, carbon monoxide electrolysis, and nitrate reduction. So in all of our works, we see that are the insights that we have, are they applicable to actually more than just our specific technology? And then you have, let's say, the bread and butter of where my group tries to focus on is problem-centered research. So we have a problem. We have, say, salt precipitation in an electrolyzer. We have flooding. We have copper catalyst stabilities are an issue. Bipolar membrane stability. So these are very specific topics, but there's a problem that's open and it doesn't work, and then we try to resolve that. And then you, let's say, have this region here on the bottom left, and this is places where work is published. It might seem interesting when it first comes out, but then after 2 to 3 years, that paper doesn't really get referenced or cited anymore because other work has superseded it. So it wasn't, let's say, it doesn't stand the test of time. That's a very brief kind of example of the novelty impact curve. Now I want to add a third axis. I want to add a risk axis. So high risk and low risk. So let's say these two boxes. High risk research, for example, would be work that's characterized by, to be able to get any data at all, you have to do, say, months of work to get the setup working. You have to design something completely from scratch. You have to wait a long time for parts to arrive. And even the worst case is if you do perform an experiment, so you have an idea and it takes months and months to set up, you get the data and your hypothesis is wrong, or the thing that you expected to happen didn't happen, and now you have a very expensive paperweight potentially. Low risk research is, you have a colleague with a setup, or you have existing setups in the lab, and then really you have an idea for an experiment and you can test that right away. And ideally, let's say you can prove or check our hypothesis in a short period of time. The other type of low-risk research is regardless of the outcome of your hypothesis. So you've chosen a research question or hypothesis such that if you're wrong or if you're right, your experiments should essentially add value. So here's where it's great. Where in this case, the hypothesis itself or the idea itself is the novelty as compared to the end resulting data. Something that's good to know for all research projects, for those who haven't been through a lot of them, is that risk only ever increases after you start a project. So you might think of something that seems simple or seems easy, or you're sure of your hypothesis, but then as you start getting data, as you start testing things, more and more problems arise, and let's say the risk increases because you've sunk time into a project. So generally, you might say start up here in the high impact, high novelty, low risk, but over time, your novelty, risk, and impact will change throughout a project. So now let's look on this with one axis. So the y-axis, we now have novelty, impact, and risk versus project length. So in general, things decrease over time. So, if you have a 2-year research project, the field might have moved on from your problem. Other papers might have come out. People might have solved your problem. So generally, risk or novelty and impact go down. And then risk might have something kind of like this shape. So it rises and then goes down. What happens here? Why does risk all of a sudden go up and then has a kind of an inflection point and goes down? What's happening at this moment in time?
Just where you develop your project actually. So during the first phase of development.
Yeah. So during the first phase, it's going up, and then what happens when it starts going down?
Then when you optimize the thing, when you get the optimized stuff, then it's stuck. Then you know actually what we should use or what we should not.
Yeah. So let's say you start collecting data, but even sharper. What's like the aha moment that happens here? I would argue that this is when. Yeah, I would argue this is when your key hypothesis is confirmed. So you really have a sharp research question, a sharp hypothesis you want to test, and then at this point you get the data that says, okay, this makes sense. All my ideas are aligned. And then from that point, you still have to collect data. You still have to make the supporting information. You still have to make the figures. You still have to publish the paper. But let's say that's when the risk can start going down because you have, let's say, peace of mind and trust that your idea can move forward. Now, an ideal research project, you want to be able to go from this, what you see on the screen, to this one here where you shift that project earlier. So any project can go on for as long as you want. Ideally, we would like a project to be shorter, not only to improve the novelty and impact, but to reduce the overall risk and stress of a project. So I would argue that here, the lighter pink line is when you have a poorly formulated research question and hypothesis, and the darker red line is when you have a well-formulated research question and hypothesis. So really, how you start a project really determines how the project will go. So you want to push that key hypothesis as early as possible. So what are some examples of poorly formulated research questions versus well-formulated research questions? I would say a poorly formulated research question is one where you have a clear problem, but no specific solution. So what we see a lot in literature on the catalyst side, for example, is, hey, oxygen evolution catalysts are expensive. They use iridium. I want to research alternatives. That's an important problem, but that doesn't exactly tell you how to solve the problem. So you're working in an area that's important, but no clear resolution. So ideally, you couple a clear problem with a proposed solution. So bubble losses, ohmic drops from bubbles in alkaline electrolyzers are a problem. I think bubbles can be better removed with pulsations. So now you have a problem, and you're combining that with a potential solution. Poorly formulated research questions are also too lofty or vague, so they're not sharp enough. And a way that I like to think about it is if you have an appropriate scope for a research question, you can kind of say at least 100 people around the world are going to be really, really interested in the result of this. Okay, so that's a nice threshold. If all of a sudden you say in my research question, 10,000 people are going to be amazed and fascinated by the result of my research, there's a good chance it's going to be a very, very hard project. And it might be, let's say, a larger research line as compared to an individual project. So that's, let's say, one way to think about a scoping. Also, if your hypothesis cannot at all be tested by literature, that's kind of a red flag to me. And ideally, you want to be able to directly test your hypothesis. So we have a really big problem in science between correlating things. So you change one operating parameter and you get a result, and then you change the parameter again, you get a different result. And you might say, oh, look, these are linked. I have a cause and effect. You very much could have a correlation of things. So you have an indirect observation as compared to a direct observation. So a hypothesis ideally is really, really testing something directly and not relying on indirect measurements to test that. Yeah, and then the last one is really make sure you know who your subfield of researchers are. So what I want to do is I want to go through some examples in my research group of 2 papers that we looked at to kind of tell you the approach we use. So here are papers I'll go into now. The top one is probably my favorite paper from my research group. It's just one where all the pieces went into place, and to me the story is so simple but valuable, and that really embodies the scientific method I think that we try to take in our approach. So this one falls into the category of what barriers prevent commercialization. So early in the scale-up or gas diffusion layer timeline of CO2 electrolysis, flooding was a very big issue. And at the time, well, a lot of researchers you talk to would kind of say, well, during CO2 electrolysis with a flowing catholyte, gas diffusion layers flood. So these carbon-based materials with PTFE, they let water through and they flood. And flooding hurts the performance. It hurts the selectivity. It blocks CO2 gas from reaching your catalyst. And people said, well, it wasn't really a problem for oxygen reduction reaction in fuel cells. Why is it a problem for us? So there was the idea that something about CO2 electrolysis is causing flooding. And people thought maybe salt is forming in there. Maybe you have salt pumping. Maybe you have gas bubbles causing pulsation, weakening the gas-liquid equilibrium. There's a lot of thoughts going around there. So we took a deductive reasoning approach. And we said, well, if CO2 electrolysis is causing flooding, then we should be able to put a different gas there, and we should be able to see a difference. So if you test with and without CO2, you should see a behavior difference. And we did see a behavior difference. So in this graph here, the y-axis is the time it takes our gas diffusion layer to flood, and the x-axis is the current density you applied. But what we saw, so I had Kylun, and at this time we didn't have a camera set up to look at the back of our gas diffusion layer. So here Kylun is actually looking at droplets of water that are coming out of the back. But what we saw was actually the opposite of what we expected. So in this case, maybe I can get my pointer. So in this case, we actually saw that CO2 caused the gas diffusion layer to flood at a longer time than if we used nitrogen. And this went against the prevailing thoughts in the field at the time that CO2 electrolysis was causing the flooding to occur. So then we switched to an inductive reasoning approach, where then we looked into our data in a different way. So we said, okay, well, there's a difference between these two. How are the voltages between these two scenarios different? That allowed us to dig into things. And what we found more or less was when you start varying the catalyst now, so now you can vary the voltage by varying the catalyst. We actually found that we can link the flooding to a voltage of your electrode and nothing to do with the reaction itself. So it doesn't matter if you're doing water electrolysis or CO2 electrolysis, your flooding is actually linked to the voltage, which is then linked to electrowetting. So here's where we did very, very, very few experiments. The paper was very, very, very short to write and has impacts not just for the CO2 electrolysis field, but for any kind of carbon-based gas diffusion layer work. The second project I want to talk about, this was a perspective from last year. And here what we talk about is really what are the effects of heating in electrolyzers. Now, let's say an electrolyzer, whether it's water electrolysis or CO2 electrolysis, we're only talking about energy efficiencies of 50 to 80%. So then where does the extra energy go? So you put in a bunch of electricity, where does the extra energy go? It goes to heat. And we wanted to say, well, how is this heat dissipated? And what happens as you start scaling up an electrolyzer? So how big is a 1 megawatt electrolyzer? Does anyone know how big that would be? I see the room you're in right now. How big would a 1 megawatt electrolyzer be relative to that room?
More, maybe one meter square range.
Yeah. So that the table, for example, that you're on, the gray table, that's probably roughly the size you'd need for a 1 megawatt electrolyzer. So it's actually smaller than you might expect. But if you have a 1 megawatt electrolyzer and you're only 50% efficient, you now have half a megawatt of heat that you have to dispel from that electrolyzer. So where does that go? And what does that mean for what the operating temperature of an electrolyzer is? So we took this approach, and here our entire key hypothesis. So essentially, how is heat rejected in an electrolyzer, and what will this mean for the operating temperature of an electrolyzer? You can do on one A4 of paper here. So here you can very, very quickly prove with some bachelor's heat mass transfer and thermodynamics, you can show that you have a really, really big heating problem of your electrolyzer. And in fact, what you can do is you can say, well, my heat that is generated has to be balanced by cooling. And here your cooling is through your advection of your gas stream, your liquid stream, and your Newton's law of cooling on the outside of your electrolyzer. And you can very, very quickly prove that almost all of your heating will be taken out by your liquid. So your gas is negligible, your surface cooling is negligible once you start getting to larger scale electrolyzers. So this allowed us to essentially say that through very little math, that an electrolyzer will really be operating in the range of 40 to 70 degrees Celsius of operation. And this was important because lab scale electrolyzers, remember I mentioned 3,000 papers per year on CO2 electrolysis? What temperature do you think those experiments took place at?
What is the question again?
At what temperature?
Yeah.
That is usually
around 80.
Sorry?
80 degrees Celsius.
That would be nice. So almost all research in the CO2 electrolysis field, so thousands and thousands and thousands of papers take place at room temperature. And that's because you essentially have a 5 megawatt cell that can easily be cooled by the environment in the tubing. And in a room even like this, our computers, 5 watts of heat, for example, is not really a problem. So you have a huge amount of literature that's being done at 25 degrees Celsius, when in reality, you will be physically forced to operate around 70 degrees Celsius, purely from a heat expulsion perspective. And this means things like CO2 solubility, viscosity, all of the parameters of your system will change. So in this work, you could essentially prove from 1 day of work on an A4 paper, you could confirm your hypothesis that even a lab scale electrolyzer should be operating at closer to 70 degrees Celsius to be relevant for scale up. And you can do this with very little background. So you don't have to do complex experiments. You don't have to have a PhD even. You can use bachelor's knowledge to do this. So this is an example where asking the right question can give you a work that is both impactful, has novelty, and is low risk. And really, all you have to do is really try to look for it as much as you can. I'll move into my closing now, and there's a few things I want to talk about the end of a project. So once you actually apply, let's say, the scientific method and deductive reasoning, this actually directly translates into your introduction for a research paper. So typically, your argumentation follows the argumentation you did when you took the research, in which case your introduction should really just flow directly from there. And that's an ideal scenario. And typically, when you run into troubles with writing, it's because your logic or your narrative is a little bit broken. So if your data and problem statement are mismatched, that's where you typically run into writing problems. So it's important to really take a storytelling approach. And then what I really like to believe is when someone's reading your paper, an editor or a reviewer should actually want to accept your paper by the time they finish reading the introduction. So you haven't presented any results, you haven't presented any data, but you have a motivation, you have a clear problem, you have a clear hypothesis that comes through in your introduction. And what you're effectively having is that the reader, your ideas are becoming the reader's ideas. And then what you have to now do is then have your data and your figures execute that and justify that hypothesis. Of course, your idea must be novel and impactful. You can't pull the wool over someone's eyes. I also saw this during my master's days. This is the gauntlet you have to go through when you have a poorly formulated research question. So it's better to have a well-formulated one. And you can avoid, if you like the Inception reference, you can avoid Mal as reviewer too as well. So how do you end a research project? I think you should end a research project as soon as your key hypothesis is proven. So as soon as you really have your primary thought, you should draw up your figure plan and try to close it. A lot of times students have the feeling of moving goalposts, and I really think this exists for 3 different reasons. So one is new researchers underestimate the number of steps it takes to close a paper. Once you have your key novelty, you still have to do all the supporting information, write up the paper, get the figures, rewrite the paper again, and people can feel it's just going on and on and on. And understanding the full process can help to remove the feeling of moving goalposts. It's also very common. If you have new knowledge and you have new possibilities, you want to do more experiments. You want to take the research further. But in a way, this can be distracting. Once you have your key hypothesis, write it up, finish it off, and your new knowledge and new possibilities can be your next project. And something that's also true, I say the aha moment is not really. I meant to rephrase this. It should be is not recognized by the PI. So sometimes we actually do science that is amazing and we've proven a hypothesis, but either the PhD student or the PI doesn't recognize this. So to some degree, you have to do some massaging to make sure everyone understands how important the research results are. So what do you do when you have new options during a project? I would say finish the paper first and then investigate your new options. At the very least, say, okay, for only 2 weeks, I'm going to work on advancing this work further. And if that doesn't work, then I'm going to make it a new project. And that's actually what we did with this work. We found why flooding is occurring. And we said, oh, can we now avoid flooding? We spent a few weeks trying it. We couldn't do it very fast. So we dropped that and moved on. First projects are so unique. So who are young PhDs in the audience or junior PhDs? Do we have a bunch of people who are, let's say, early in their PhD careers? Yeah, a few hands up. Okay, listen very carefully to this one if you don't know. So at least in the Netherlands, a professor gets a grant. And a PhD or a postdoc is tied to that grant, so it funds the grant, for example. That means we write a proposal. We submit that proposal to a funding body. So, for example, the Dutch organization or the European Union. That grant then gets awarded, and we go through a hiring process. Then the start of a PhD or a postdoc gets hired, and this little paper here, for example, is the grant document, and we give that to you, and then research starts. But what you should know is that this takes roughly 1.5 to 2 years from the inception of an idea to someone literally starting in the lab. And what is natural in science is an idea fades over time. So it might be bright at the beginning. It might sound amazing on paper, but more and more research is published. Maybe thoughts or interest wanes or the novelty wanes over time. So it's important to know that what you get at the start of a project is different from when it was conceptualized. So you can't always choose your first project, but what you should always do is update the research idea to account for what has happened in the field. And if absolutely nothing has happened in the field in over 2 years, why is that the case? You should ask the PI or ask your professor, why has nothing changed? You should also seek what has changed in your own supervisor's perspective or what research has taken place. So there are ideas that I think, you know what, I still believe in this idea, but I'd actually rather do it slightly differently. It's important to not just follow a grant. So just like a PhD thesis proposal looks nothing like the final thesis, the output of a grant usually doesn't look like what was proposed in the grant document. So PhDs and postdocs should recognize this and then, yeah, try to adapt a first project for what's changed over time. What's also very important is make a research question your own. Even if you can't control what the research project is about, it's important for you to make that project your own with your own strengths and potentially avoiding your own weaknesses or trying to improve on your own weaknesses. Because really, if as a researcher, you're not involved in the idea generation stage, or you're not invested in the project, then your interest will wane over time. So in brief, please use the scientific method as much as you possibly can. And I really encourage you to test your hypothesis versus literature. In most fields, especially in the electrochemical domain or in the energy domain, there's so many researchers working on it. There's a good chance someone has indirectly done the experiment that you would love to do. So really dig into their data with your new perspective and see if you can test the hypothesis before you have to actually test it in the lab. And really try to shift your key hypothesis as soon as you can. So I firmly believe that data is only as good as the idea that you have for that. So ideas lead to more novelty and impact than data. So our group really publishes a lot of papers where we might only have 50 to 100 experiments, let's say in a singular paper, including all the supporting information, main figures. I really think that that's a lot easier than generating thousands of data points and looking for a narrative. So thank you for listening to my spiel. Here's the wonderful people in our group who do all of the work actively, our funding sources, our collaborators, and a couple of references for what I talked about today. So thank you for your attention.
Thank you very much, Thomas, for this excellent and insightful talk. I think we are, I'm sure that we have learned quite a lot about these different approaches to tackle the research problems in electrocatalysis and even beyond. Now the floor is open for questions.
One question in the chat.
Yeah, I will just, please write your questions so I can read. So, wonderful. Just let me check if there is
that one, yes.
Okay. Okay. The first question is: can you comment on the future of high temperature electrolysis? For example, solid oxide electrolyzer. Thanks.
Yeah. So I'm looking down because I can see the chat here. Solid oxide electrochemistry is really quite interesting. So let's say what Topsoe is doing for CO2 to CO electrolysis, and I think Zio Hu's group in EPFL also has some really great examples of that. Pretty much CO2 to CO via SOECs is really the most energy efficient way to produce carbon monoxide, and a lot of, let's say, the issues around, say, nickel sintering have been solved. I think that scale up and intermittent operation is still a very large challenge, but from a sheer energy perspective, which is really the biggest barrier for any kind of electrochemical technology, I think SOEC CO2 to CO is quite interesting. SOECs do have the challenge that you can't make multi-carbon products, so you can't make things like well, you can't really make methane, you can't really make ethylene or ethanol. So that's one shortfall, but SOECs are quite interesting.
Okay, so the next question, I'm just going to read the question so that the audience also can understand. So wonderful talk, Professor Burdyny. According to you, what are the new problems in electrochemical carbon dioxide reduction we should work upon as a new researcher to this field? Shifting from water electrolysis to electrochemical carbon dioxide conversion.
Yeah, so maybe I'll try to shotgun approach the problems that I find really interesting. So copper stability. So being able to produce ethylene and ethanol is only really possible at high rates with copper catalysts, but they're extremely unstable, both from let's say a more facet perspective, but also a micro scale perspective. So copper stability is quite interesting. The holy grail would be if you can do CO2 electrolysis in highly acidic media via a mechanism that doesn't use water. So right now, all CO2 electrolysis requires water as the proton donor. And this means that your local pH gets shifted up, and it really confines CO2 electrolysis to a minimum cell voltage, even at low current densities of 2 volts. So water electrolysis, you can get current, meaning like you can get amps of current density at 2 volts, whereas CO2 electrolysis only starts at 2 volts because you have local Nernstian losses. And yeah, CO2 is an acidic gas, so you can't do an alkaline media. So if you could cause CO2 electrolysis to occur at pH 0 or pH 1 using protons as the proton source without having water electrolysis take over, that'd be a really big breakthrough. But all research has shown that you need water as a reactant so far.
Okay, so the next question is, what is the main product of CO2 electrolyzers and how you are tackling the separating problems associated with it?
Yeah, so if you're making carbon monoxide with CO2 electrolysis, your byproduct is almost exclusively hydrogen. And then you don't really need to separate the CO and hydrogen from that, because then you have syngas, which can be used for downstream process. Any carbon monoxide process will require hydrogen to be added to it. The bigger challenge is actually separating CO2 from there. The best thing to do for that would be to have conversion as high as possible, and then essentially do, let's say, maybe a caustic CO2 removal. If you're making things like ethylene or ethanol, that's where things get more confusing. So for ethanol, you really want to encourage things to come off in the gas phase if you can, and then you can condense out the ethanol. But right now, separating ethylene from the gas phase is extremely challenging, because almost any kind of way separation method you use, things are poisoned by CO. So there is, let's say, some interesting separation work in this field, but it's really a mostly neglected domain.
I would have one question as well. So if you look a little bit at the field of water electrolysis, you can see that it is facing a lot of hurdles to go towards industrialization, because the costs are higher, the performances are lower than expected. What can the people working in the field of CO2 electrolysis learn from these hurdles? Do you see similarities that you can take benefit of this experience of water electrolysis?
Yeah, so CO2 electrolysis is a funny field. So the challenge is, if you look at renewable electricity generation, there are about 15 years of places we should use renewable generation before we actually put it into electrolyzers. So electricity is increasing. So what I'm trying to say is we have a very large amount of time to, let's figure out some of the challenges for CO2 electrolysis. But the problems that we're starting to see is that it's always going to be harder than water electrolysis. We're always going to have more degradation mechanisms, and the voltage will always be inherently much higher. So right now, what's interesting is that through CO2 electrolysis, we've been able to train a large amount of researchers and been able to develop a lot of different new materials that are then applicable for other electrochemical technologies. But it's hard to say at this point if more or less low temperature CO2 electrolysis is really the best option. But it's acted as a very good platform for advancing technologies and training researchers. I could only hear part of your question, but that was what I thought was the gist.
Yep, okay, thank you.
Any further questions?
I see one from Robert, who I corresponded with a few years ago about a paper.
Yes.
It's good to have you connected, Robert.
Yeah, I'm just reading that. The more established electrolysis field have clearly defined DOE targets, or some other targets established by the consortia for catalyst uses, current density, and other performance metrics. PEM fuel cell have such targets, and also hydrogen production by water electrolyzers has clear price targets. Are we going to see such clear targets anytime soon for carbon dioxide reduction reaction, given it gets more traction in pilot scale and attention from investors?
I don't think so for two reasons. One is the current political climate as well as let's say the generalized economic downturn, which is let's say made water electrolysis even less of an interesting or favorable topic for governments and industry. So that's one aspect. The other side is CO2 electrolysis it's an embedded technology. So water electrolysis, you can have lots of justifications for it only has, let's say, a one downstream technology after it relying on it. But CO2 electrolysis, you need a CO2 source, you need your electricity source, you need a separation unit, and then you need, let's say, typically a downstream thermochemical conversion process. If you make CO or you make ethylene, you have to do downstream processing. So I think it's such an embedded field or topic. I don't think you'll see things like DOE targets anytime soon, or even if it's not in the United States, but I don't think you'll see government targets anytime soon.
Okay. The next question is, what improvements can we make with the catalyst, electrolyte, or solubility of carbon dioxide to improve the C5 plus product Faraday efficiency?
So, yeah, here I do want to ask if this is this a C5 or C2?
I was also.
Yeah, because well, maybe I'll so there was a wonderful paper back when I was doing my PhD. It was called What Should We Make with CO2? Or it was by Alexander Baranov. More or less, it looked into the amount of electrons you need for different products. And the thing is, as soon as you start making things like propanol, which is a C3 product, you require 18 electrons. But your energy density versus C2 or C4 products is minimally, very, very minimally gained. So unless you're making a very, very useful niche product that has extremely high versatility and can't be made by other means, you shouldn't sink that many electrons into products. Even ethylene and ethanol, there's a very strong argument to be made that even those require just too many electrons to make. The only reason they're still interesting is the alternatives for making them are really not interesting. But to go from CO2 to C5 products, you're talking about, I think, say 30 electrons. There are researchers in the microbial electrosynthesis field who makes things like caproate or hexanoic acid or hexanate. Those are very unique products, and those might have a small market size that then justifies the electrons. But mass market chemicals like carbon monoxide or ethylene, you don't want to go to high electron uses.
Okay. The next question is, do you feel that in the field of carbon dioxide conversion, there have been lessons or techniques borrowed from adjacent electrochemical reactions that may have slowed down progress in CO2 reduction? If so, do any examples come to mind?
Yeah, I think there's some things that in hindsight, yeah, I actually have a separate talk where I go through the history of CO2 electrolysis, especially the modern day history, and it's really a fascinating field because 12 years ago we were doing CO2 electrolysis at 0.1 milliamps per centimeter squared on a 0.1 centimeter squared electrode, and we'd be excited about 50% Faraday efficiency to carbon monoxide. Like the field has advanced so far in 10 years, it's hard to say what has slowed things down or what mistakes we have made. But there's a few things where we made assumptions that were wrong. So when we switched to, say, membrane electrode assemblies, for many, many years, it didn't work because we were using amine membranes that were designed for hydroxide as the charge carrier. In CO2 electrolysis, any hydroxide we make from water reduction immediately gets converted into carbonate because we have so much CO2 that's present there. And carbonate is a completely different charge carrier than hydroxide. And it took way too long to figure out that that's what's preventing MEAs from working. So I think the problem we might have had is a lot of people came from, say, the water electrolysis field or the let's say more fundamental catalyst field, and then completely neglected all of the work in the 80s and 90s on fuel cells or PEM electrolyzers that would have accelerated CO2 reduction even faster. So I'm very, 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 very happy with what's happened in this research field in 10 years. It's really astonishing. And that's because we borrowed architectures and gas diffusion layers from other fields, but we didn't transfer some of the engineering knowledge with it. So I consider the 2020 to 2021 kind of a dead era where things should have moved faster.
Okay, any further questions? I actually have a couple of questions, Thomas. So when we talk about novelty and implementation, so let's say we are designing a project or we are just trying to define our goal for a specific, maybe let's say we talk about carbon dioxide conversion. When we talk about novelty and implementation, what is like how it is defined? So how we can define novelty? Or when we should get like satisfied, okay, this should be novel enough.
Yeah, that's tricky. So you can, let's say, if you don't understand the research field, enough, then because what matters is kind of what the collective people view as novel. And you, let's say, need to meet over that threshold. And if you don't have a good view of literature, then it's hard to do that. The other problem is when you've been working on a project for a while, to you, it becomes not interesting anymore because the light bulb moment has already happened for you. So something you now view, something that's internalized in your own knowledge foundation, you don't know isn't in someone else's knowledge foundation. So what I like to think of is I think where I've been successful as a researcher, I feel that I've always had the pulse of the field, of the research field. So I don't go to a huge amount of conferences, but I feel like I know the momentums, I know the researchers, I know what people care about, I know how things are kind of moving in different directions. And by having that kind of pulse of the field, I think you have a good idea typically of what's novel and what's not novel. So it's not just reading literature, but also seeing trends and where things are going.
Okay, thank you. We have another question from the audience. Do you see the possibility of circulating H plus and bicarbonate ion externally, trying to balance ion concentration and prevent salting and severe conditions in each components, or each compartments? Sorry.
So H plus. So I guess like what you've seen a lot in the field is people using, say, alkaline electrolytes to let's say, and that can actually inhibit some failure mechanisms and reduce voltage, but you're artificially causing a system to be stable. So when you say circulating H plus and bicarbonate, I don't know I don't exactly know how this would be done, maybe in the cathode channel. But anytime we're doing, let's say, one of these kind of custom or unique configurations of electrolytes or layering of different things, it's very important that we make sure that we're not artificially increasing the stability of a system or artificially introducing energy into the system. So, I mean, the only reason why KOH gives you, let's say, really, really low cell voltages is because you're artificially imbalancing the system and pushing the reactions to favorable conditions, but you're consuming KOH in the process, which itself requires energy to create. So I think that the work that's done in acidic CO2 electrolysis, there essentially they avoid the carbonate generation problem. So you lose CO2 to carbonate crossover, which then is released at the anode with CO2 as CO2 and oxygen together. The acidic case where you put in an acidic catholyte, that removes that carbonate crossover problem, but it doesn't really prevent the salt precipitation. The best way to avoid salt precipitation is higher temperatures and making sure that liquid water doesn't evaporate and then leave salt.
Okay, maybe the last question from the audience. What are the new ways, according to you, to increase the solubility of carbon dioxide in the solution at such a high temperature of 70 degrees Celsius?
Yeah, so I'm not too worried about solubility, and this comes down to two things. One is Well, there are several works, for example, that show that you can get up to 1 amp per centimeter squared at 60, 70, 80 degrees Celsius. So demonstration-wise, that's kind of been shown that solubility is not too much of an issue, but it's mainly because you get down to a mass transport perspective. So you have CO2 gas that is diffusing into a liquid layer, and their solubility has actually never really been the limiting factor. It's actually how far that CO2 diffuses. So if you have the oxygen reduction reaction, for example, the solubility of oxygen is 30 times lower than CO2, but you can get up to 1 amp per centimeter squared. So it's less about solubility and really about controlling your gas-liquid interface so you don't have to diffuse several microns to reach your catalyst layer. The other aspect is most research is done at room pressure, ambient pressure, 1 bar. But if you scale up to a megawatt scale electrolyzer, your CO2 is going to come in pressurized. You're probably going to want pressure for your separation process. You get kind of free pressurization of your products if your feeds are pressurized, semi-free. So in reality, we'll actually be operating any kind of commercial system at several bars of pressure, which then helps with your solubility aspect.
Okay. I have my second question is like when you were talking about this flooding phenomena, so in your SCS energy letter paper, like the voltage increment, it also leads with like flooding of your electrolyzer. So was it literally connected to voltage, or when you are increasing the voltage, your performance of your electrolyzer is getting higher, and then maybe there is vigorous gas bubble formation that makes the electrolyzer like not that tight? Is it?
So what we linked it to was on a carbon-based support. When you kind of get to this minus 0.65 volts per RHE, you actually your surface of carbon undergoes a change, and you essentially go to an electrowetting potential. So your surface functional groups essentially lead to one that is now wetting. And the way that we confirmed that it was that occurring as compared to some kind of bubble or activity-related phenomena is we changed our catalyst, so the exact same current density, but we changed the catalyst between ones that have different potentials. So copper and silver have relatively high potentials for hydrogen evolution. We saw those flood, but then we switched it to platinum. We did the exact same current density, and platinum went for, let's say, 5 hours or so without flooding. So we actually even increased it to 50 milliamps per centimeter squared, which is still below the electrowetting potential, or still more anodic than the electrowetting potential, and we still didn't see flooding. So there we were able to link it to voltage and not activity. That was one of those control experiments where when you think how do we have a hypothesis, we see it's happening, how do we prove it's happening? That's one where you change the material, you keep everything else the same, and all of a sudden you don't see flooding. So that's where I love control experiments. When you have a hypothesis and you're sitting there with the PhD or the postdoc and say, how do we prove this? Coming up with crazy control experiments that show it is my favorite activity.
Great. Okay. Is there any further questions? If not, then let's give a big round of applause to our speaker. Thank you. Okay, before we close today's event, please allow me to have a few closing remarks. So big thanks, Thomas, again, for accepting the invitation and for this excellent lecture. This was the inaugural lecture of our seminar series.
And thank you for having me.
Thank you so much. I would like to thank all my amazing colleagues for their constant help, encouragement, and support. Last but not least, sincere thanks to all of you for joining us today and for making this inaugural lecture a success. So we'll be announcing the second lecture of our seminar series within the next few weeks. Please keep an eye on our departmental webpage as well as our LinkedIn page. That's it for today. Thank you so much. Thank you.
Thank you. Bye, everyone.
Bye-bye.